What's going on, guys? My name is Hussein, and in this video I want to discuss indexing, database indexing. It's a very interesting topic, and I think every backend engineer, specifically if you are involved with databases and relational databases or any kind of databases, you need to know what indexings and how indexings work and what is the benefit of indexing. So in this video we'll describe what is indexing. We're going to work with indexes. We're going to work without indexing. And we're going to see how the performance differ whether you have an index or you don't have an index. So first of all, what is an index, guy? An index is a data structure that you build and you assign on top of an existing table that basically looks through your table and then tries to analyze it and summarize it so that it can create kind of shortcuts, right? The best way I can think of an index is like, if you know these, if you ever seen a secretary's handbook or phone book where you have like thick, big book and it is labeled. There's like a label color with A, B, C, D until Z, right? So the letter A starts with all the company's phone books that start with the letter A, and B start with all the B's, right? And C is all the C's. So if you want to look through find a specific company name, phone number, and you know it's like, oh, it's I don't know, it's called Zebra. So you go to the Z, right? And then you start searching there. That's the simplest thing I can think of the index, right? And basically the index, guys, are two types so far that we know of. Something called B tree and LSM trees. And I'm not going to go through the depth of how they are constructed. This is outside the scope of this video, but essentially it's a data structure and you can look it up. It's basically allowing you to search very effectively, right? And you find quickly what you're looking for. So guys, here I have a table called employees with around 11 million rows. Okay, it's a quite large table. Okay, so I have an ID field, is integer, it's not null, and it's sequential. So every time I insert a row, I don't touch this field. It will automatically insert and increment the value. And it's also a primary key. That means unique, right? And it also has an index by default. Every primary key has an index by default, and it's a B3 index, right? So that's what I have here. And I also have a name field on this, which doesn't have an index. It's just a bunch of characters, nothing fancy. It's not really the actual name. I just spent some time generating 100 million random strings, right? So now if I, for example, do let's clear this up and do select ID from employees where ID equal 1000, I will return the thousands ID, right? That's not fancy, right? So if I do select star, I will get everything back, ID and name, and N1 is the name. So don't pay attention to the actual name. It's just a string, and that's the idea of the string here. So guys, what I want to do here is I'm gonna go through steps of different queries. I'm gonna show you the performance of each of these queries, right? In order to do that in Postgres, that's the database I'm using, by the way, Postgres, I'm gonna do explain analyze, which will actually explain the query that I'm gonna do, and it's gonna tell me how long it took, right? Which is really neat. So I'm gonna do select ID from employees where ID equal, let's say 2000, because the first one is cached. I don't want to mess up the statistics. All right, so what happened here, guys? Let's decipher what happened. It says, okay, your predicate filter, you're trying to find ID 2000. That's the employee with ID 2000. In order to find that, I didn't go through the actual table 11 million and I searched sequentially. No, I actually scanned the index, which is way faster because the index is always smaller than the actual table. because it tells you, okay, it is structured in a way so that if you search, and I'm gonna put an animation here a little bit so you can see, like if I want to find ID number 2000, it starts searching. Okay, 2000 is between 4000 and 1000, so it was okay. Let me go to this tree. So it goes, you go to another tree and then search from another between this number and this number. So until you actually find the number, right? That's how B trees basically work, right? So now what I did, I only scanned the index, which is very, very effective, right? Heap fetches, that's another interesting thing. So it says the value that I actually queried, which is the ID, I did not have to go to the heap to fetch this information because the ID, since that's the only thing you're selecting, is in the index. So I just pulled it inline. That's called inline query. If the information is available in the index, that is the sweetest query to a database engineer. If you can put as much information as you can in the index, so that as I scan the index and you only select the ID, that is the sweetest thing you can do. So the whole thing took 0.6 millisecond, and to plan the query and to study what we go through, the fact of, oh, should we use the index or should you scan the table, is a query, is a decision, and that's called the planning time. The execution is the actual work to go and do the work. All right. So let's spice things a little bit. What I want to do here in this case, I want to select 3000 in this case, and you can see that took 0.1, 0.8. What I want to do is I'm going to change the ID 5000, and instead this time I'm going to ask for the name and compare the cost here, guys. Look how long it took. So selecting only the ID, where you know the ID, which is like a silly query, if you ask me, right? It's a little bit of a silly query because you know the ID. Why are you just selecting the ID? But it's just for science, guys. We're doing this for science. So it's pretty cool, right? It's 0.1 milliseconds, less than a millisecond, which is quite fast. However, when we actually selected the name, which is a column in the table, it is not, the column is not in the index. It is in the table. It's in the heap. It's in a different data structure, right? And in this case, it took us 2.5 milliseconds, not seconds, 2.5 milliseconds, which is quite fast, but it's still, database speak, it's a little bit slow. This is a slower query, and you guys need to understand when you execute these queries what it does really mean. Because I found the ID in the index, but I had to jump into the table row on disk, which is a different structure, by the way. The table is in a different place than the index. The index is a data structure and the table is a different data structure, right? Table is actually the heavier thing. We try to avoid going to the table as much as possible because there's 11 stinking million rows there. So we try not to touch it as much as possible, but sometimes we do. So what we did is we found the ID and then we actually try to go and seek to the disk. I mean, I have an SSD, so there is no seek. We go to the page that has this information and we retrieve it from disk. So that's another read from disk. So it's a little bit slower. It took us 2 milliseconds. And obviously, if I execute the same thing again, it's faster. Why? Because caching. Because we cache things. Cache, there's so many caches going on. SSD caches, the control SSD caches, the database caches, everyone caches. So God knows why is it faster now, right? But that's why, because I'm executing the same query. But if I change this to something else, I might not get it right, but you get the idea, right? 2 milliseconds again. All right. So now let's spice things a little bit. I'm going to do explain, analyze, select ID from employees where name is equal ZS. Let's do it. Ooh, guys, are you feeling it? You feeling it, right? That was slow. That was deeply slow. Why? Because guess what? The name column does not have an index. And that means the only way to actually search through the name, the value ZS, is to actually go one by one and do a sequential scan on employees table. That's the worst thing. It's called the full table scan. You want to avoid full table scans as much as possible. However, Postgres tries to be a little bit smarter by executing multiple threads, worker threads, and does the sequential scan on parallel, which is still good, right? So the planning took 0.83 millisecond, which is not much because, well, does this column, which is the name, equal this filter? Does this have a where clause? Does this have an index? Nope, it does not have an index. Move on. Full table scan doesn't have a choice. All right. So it went through and scanned 11 million rows. Well, not necessary. Well, no, yeah, it is necessary. You have to scan the whole thing. Otherwise, how do you know that all of them, right? You have to check every single one of them, which is the slowest thing. How long did it took? It took 3 seconds. Yikesy. That is so slow. Yeah, so it is pretty slow, guys, to do this. Another thing that we notice all the time is I used to do this all the time without knowing. There is a command in SQL called like. Like if you don't know, hey, is ZS before and after? You just add this percentage like. This is the worst query. Why? Because it is literally has to go through all the rows and does matching in this case, right? It doesn't really matter because we don't have an index, but I'm going to show you with an index how does it do, right? So what this does is it will return all rows that have anything at the beginning, anything at the end, but has to have Z capital S small in the middle. Slow. Took 1.11 second to do all that stuff. But yeah, still 11 million row, but we had 2 workers to do the work for us. All right, guys. So what I want to do here is actually going to create an index on, I'm going to name it employees name on employees, and it is on the name column. So this was going to take some time to create. Why? Because guess what, guys? It is building the B-tree bitmap index on top of all the stuff, right? So it has to fetch all the 11 million rows and then does all this magic to actually create the fancy index. So let's wait for it. All right, guys, we finished creating our index. So now let's try the same query that we have done, just without the like, just directly equal. So now, if I do this query, look how fast it is. Still a little bit slow, 47 millisecond, but damn, that was quick. Why? Because now we're doing a bitmap heap scan on employees, right? So we're using the actual bitmap index scan on employee's name. So we're actually scanning the employee's name index that we created. And this is way faster because we have fewer rows to work with, and we're gonna actually jump between few rows until we find exactly what we're looking for, right? And obviously, guys, the same thing applies where, hey, if you only pull the name, which is already in this index, is gonna be faster than pulling the ID and the name. I'm not quite sure about this. Maybe this actually doesn't hit the heap because the index, the primary key, I know this is in MySQL, I'm not sure about Postgres, but the primary key is usually stored with every single index in other databases, right? So the name index here, the primary key will be stored. So pulling the primary key from the name index will be fast because it's right there, right, with it. So however, if you have more than other tables, then we had to go to the table structure, and that will be a little bit slow. All right, guys, so what will happen if I add like here? What do you think will happen? Back to the slow query. Back to the exact same slow query, guys. Why? Let's clear this again. Let's do something else. So we don't have hit the cache. Look at this. Back to the same slow query. Why? Because we could not scan the index. Why? This is a lot of people make this mistake. Yeah, the name column has an index, but what you did is you're not actually asking for a literal value. You're asking for an expression, and there is no index that will satisfy this expression, because we cannot search the index on this expression, because this is not a single value. So the planner quickly detects this, says, okay, planning time, we check, less than, oh, sorry, the filter sucks. And that's why you have to explain on your queries and see why are they actually slow. Because of this. Because look at this. We did a parallel sequential scan. Again, parallel. Not all databases do parallel scanning, by the way, but Postgres do. We had to do it. We had to go to the stinking table and scan my 11 million rows. If I have a billion rows, it's going to be even slower than that. So yeah, going through all that stuff, and I'm going to explain all this number in another videos, because I don't want to make this video longer than that. I'm going to make an advanced video discussing these actual numbers, what do they mean, all that stuff. But yeah, we did a parallel scan on employees, guys. Look at that. It's so slow. We couldn't do inlining. We couldn't do any optimizations. This is an expression, obviously, so that's we had to do all that stuff. So we took a hit. We took a hit, despite us having an index, guys. Despite X having an index. So, guys, that's very quickly indexing in a nutshell, in a very, very quick video. I wanted to explain of that. Yeah, having an index does not mean that the database will always use it. It's gonna plan, and according to the planner, will decide to use the index or not. It's up to you as the engineer who's executing queries against the database to actually give hints to the database to actually use the index or not, right? This is a bad query in general. Select star is a bad query in general. Why? Because if you think about the cost to go to the actual disk and pull all the information, that is expensive, right? Really depends on how much. Like, let's say you have a blob on a column on the field, on the table. That is expensive to pull up. So if you don't need it, don't ask for it, right? And only ask for things that are absolutely there. And if you can, ask for things that are in the index, right? I'm going to talk about that in another video, where there's like multi-column index, where you can add other columns in the index that you're about to create. This is called inlining, where as I search my beautiful index, my neat, efficient index, I want the name, for example, right? That's a bad example, but I want the name. I am searching for the ID and I want the name. Oh, the name is right there. It's just literally sitting in my index. So I just pull it and retrieve it to the user. I don't have to go back on disk and find the location, seek in disk, if that's a mechanical drive, or pull the page in case of SSD, guys. All right, guys, that's it for me today. I'm going to see you in the next one. You guys stay awesome. Goodbye.